Yeah, welcome back. Sorry for the lost connection. So coming back, uh, I had to explain you about the two velocities concerned with the waves. What are the two velocities? So whenever you're given this equation y is equals to a sine kx minus omega t, I'm sure you would have seen this formula. K is equals to omega by v is equal to 2 pi by lambda, which is your wave number basically. So v is equals to omega by k. This v is in meter per second. It's some velocity. But you would have also seen this dy by dt term, which is equals to a minus a omega cos kx minus omega t, right? This, so like, what is that? This is also velocity. What is the difference between this velocity and this velocity? So what's happening here is you had a wave. I told you that in actuality the wave is not moving. It's only the particles which are vibrating, right? And their vibration, when accounted for in a very small amount of time, gives you the feeling that the wave is moving ahead with this velocity v. If you have a minus sign, then the wave moves from left to right, and if you have a plus sign, then it moves from right to left, right? So this v that you see here, it's the velocity of the wave, which is given by this formula, omega by k. It is the velocity of the wave which is actually not moving, right? So to us, it seems as if the wave is moving with this velocity v, right? So this is the wave velocity. So what is this velocity? This velocity, as you can see here, this velocity also depends on x and t, right? It also depends on x and t, just like your y. Just the way y depended on x and t, this v also depends both on x and on t, right? This velocity is the velocity of the particle. So naturally, can you answer this question? Along which direction will this velocity be? This velocity will be along the y direction, because the particles are vibrating along the y direction. And to get a particular velocity, I'll have to give in x as my input, because what is x? I need to talk about, when I talk about the velocity, I need to tell which particle am I talking about. To fix the particle, I need to go to that particle which is given by your x. And I also need to tell, because the velocity is changing with time, right? If it's because it's going to some maximum position and then coming here and then going to some maximum position. Basically, all of these particles are doing SHM along the y-axis. That's why if I fix a time t, or for example, if I fix an x, then the equation becomes like this: a sine. If I fix x, then this becomes a constant k minus omega t. So this is the equation of an SHM, right? A sine omega t plus phi. Each of your x is actually doing SHM. So in SHM, you know that when the particle is at mean position, it is having maximum velocity. This is your mean position. When it is at the extreme position, it has zero velocity. When it is at the other extreme, it has zero velocity. So velocity sinusoidally keeps varying. That means at a particular time, the particle will have a particular velocity. So it is also dependent on time, right? That's why you have both x and t. So if you want the particle velocity, you will differentiate y with respect to t. But if you want the wave, and this particle velocity is different for all particles at a particular time, right? So the particles which have the same particle velocity are in phase, and which do not have the same velocity are not in phase, right? So different particles might have different velocities at a given instant of time, or the same particle might have or will have different velocities at different instances of time. Understand the statement, keep replaying this. But this was about particle velocity, but the wave velocity is fixed for the wave. It is no way concerned with the particle. It is concerned about how is the wave seeming to move, right? So this is not changing with time, and this is fixed for the entire wave, right? So I hope you have understood the difference between the two. We'll solve a few problems now. The first question goes like this: which of the following represent a wave? So A, x minus vt square, B, ln of x plus vt, C, E of x minus vt square and d 1 by x plus vt. So such questions can be more than one correct also. I don't know if all of them or some of them or only one of them or none of them represent a wave. What were the two conditions that I gave you for any y is equals to f of x comma t form? Basically each of them is a y, right? Each of them is a y. Each of them is a function of both x and t. So this is f of x comma t. Now if y has to represent a wave motion or a wave equation, what were the two conditions that I gave you? The first was dou square y by dou t square is equals to some constant into dou square y by dou x square. This has to be satisfied by the wave, right? And the second was at no x comma t, y should go undefined. If only if both of these conditions are ensured, I can say that a y is equals to f of x comma t form represents a wave equation. Let's look at the first one. Y is equals to x minus vt square. It's very evident in this that if I put x equal to infinity or if I put t equal to infinity, then y will be undefined. So like y will keep on increasing, right? So at no x or t, my y should be undefined. So here it is. So the second condition I can say is not obeyed. So this does not represent a wave. Let's look at the second one. The second one also has the same issue. ln of x plus vt. If I put x or t, any of them as infinity, then log of infinity will actually be infinity, right? Because this is the way a log graph looks. So as x tends to infinity, y also tends to infinity, right? Y also keeps on increasing. So here also this cannot represent a wave motion because the second condition is not obeyed. Let's look at the third condition. Third equation. So always try to verify the second condition first, because the first condition you have to differentiate and then like analyze the function. So like it's always better, it's easier to verify the second condition first and then verify the first one. So let's verify the second condition for this. So if I put x equal to infinity or t equal to infinity, then y will be something like e power minus infinity form, which is 0. So like y is finite, it's not infinite. So this can represent, so it is obeying the second condition. I'll have to check for the first condition now. Let's look at the fourth option also. For the fourth option, if I put x as infinity, or if my x tends to infinity, or if my t tends to infinity, tending means it is tending to a very huge value, then y will tend to 0, right? Because 1 by infinity will be close to 0. So here also it is, even this is obeying the second condition because it's not becoming infinity for any of the x and t, right? If I unless if I put both of them 0, right? That I shouldn't. Frankly, you can say the second condition is not obeyed, because if you put x equal to 0 and t equal to 0, that means if I talk about the 0th particle at t equal to 0, it is at infinity, right? So this, in fact, the second condition is not obeyed, you can say, right? So it's not. So third is a possibility, but I'm not sure if third represents the first, obeys the first condition or not. So for that, I'll have to differentiate and see. So what I'll do is I'll first differentiate with respect to time. I'll do this dou square y by dou t square. So differentiate this with respect to time. So I'll differentiate it once with respect to time. X minus vt into minus v. This is e power 2v into x minus vt. And I'll differentiate it once more with respect to time. So this was the first derivation. The second is first differentiation. The second one is similar, minus 2v square into x minus vt. Right. Now let's look at dou square y by dou x square, and that is I made a mistake here. This is into v, right? Not to the power. It is into minus v. So you'll have a minus here as it is, and then one more minus v will come. So this v square is actually here, right? So when you differentiate, the v doesn't remain in the power. It'll have to come. It'll have to multiply this function, right? So you finally get v square into e power minus 2 into x minus vt when you differentiate this function twice with respect to time. right? In fact, you won't even have this lack of space. I'll actually make more space and do it.